Hello and welcome. You know what? It's been a minute. We're going to do some reviewing. Chapter 8. I'm going to do 10 example problems. Well, actually a little more because they have some A, B, C, D things as well. But they're all based on, well, they're not all. But a lot of them are based on quadratic functions. That's the huge highlight of them. There are some that are systems of equations and sequences and linear, just things like that as well. But quadratic functions is the highlight of this. Starting right now, factor and use the zero product property to find the roots of the following quadratic equations. I got A, B, C, and D. Okay, I'm going to start off with A here, and the only thing that I'm going to do is start with this square, the generic rectangle, and the diamond. Now, this is something that we've been practicing by understanding area of rectangles. Okay, if you have multiple small areas here, you can add them up and get the entire large area as well. There's also a pattern that we noticed when factoring and doing these things here, that if I have my x squared terms in one corner and the opposite corner has to be the constant term. Now this term right here, this -7, is a sum of these two numbers here. Whatever this is plus this gives me -7. And there's a lot of different numbers that can give you that. But there's only one set of numbers that gives you -7 for a sum and a product of whatever the product of this number 1 times this number 12 is. Now 1 times 12 is 12. And what's true is that when I multiply these two numbers and I get 12, these two numbers should also multiply to get 12 as well. It's just a pattern that we've picked up over time when it comes to factoring. And honestly, there's no other reason for this visual reference here. There's small things for this visual reference here that really does have connection with rectangles, but that's the big one. I'm going to write a 12 up on top here that represents product, a -7 down here that represents sum. Two numbers right here that we don't know that we will find by trial and error, guess and check, or conditioning through repetition, that when I multiply them I get 12 and add to get -7. Here's what I'm going to do. List products of the number 12. 12 times 1. 6 times 2. 4 times 3. And that's it. For integers. That's what we're trying to find, two integers for this thing. Otherwise we deem it unfactorable. Now, if we added immediately 12 plus 1, 6 plus 2, and 4 plus 3, none of these would actually equal +7. Okay? Excuse me, -7. This equals +7, right? 4 plus 3 is 7, yada, yada, yada. But I need it to equal -7. So what you got to do from here, really, the issue is that I tried 12 times 1 is 12, 6 times 2 is 12, 4 times 3 is 12. There are three other pairs of numbers that I could multiply together to get +12. That's -12 times -1, -6 times -2, and -4 times -3. Those all equal +12 as well. So what you want to do when writing out these factors is you first list them out, and then you decide, is the product positive or negative? This product is positive, which either means both numbers are positive or both numbers are negative. Because the sum is negative, I know that both these numbers have to be negative that I'm going to test here. So, what are some possibilities? -13, -8, and -7. It looks like -4 times -3 is +12, and -4 plus -3 is -7. These are the two numbers to which I'm referring here. Now, one thing that I'm missing in my diamond that I probably should be doing, but otherwise it's just a little too, it takes a little too much to say. This isn't just 1 times 12. This is 1x squared times 12, which gives me 12x squared here. And this isn't just -7, it's -7x. So technically, the two numbers that add to become -7x are -4x and -3x. -4x times -3x is +12x squared, because x times x. So the true numbers that actually go in here are -7x, -4x, and -3x. Okay? Now, does it matter which order I put them in? No. I could put -3x here, -4x here. Now, the next goal is to figure out what the factored values are out here. You really break it down per individual rectangle here, or in this case, a square. What I know here is that the area of any rectangle, like this one here, is base times height. And the thing that I'm trying to look for is something that is a non-fraction based answer here when I write this out. Well, 1x squared can be a product of 1x times 1x. I don't really need to write the ones there. I could just leave it as x times x, right? If these ones are gone, whoops, a little big. If these ones are gone right here, nothing's lost, except for part of my x apparently. So this is x times x. Right here is x squared. All right. Now, as I do that, understand that in a rectangle, opposite sides are also equal. If this length is x right here, then this length is also x. So I could write an x up here because I'm going to do x times a number here to give me negative 4x. That's going to be negative 4. So what I often don't do is I often actually don't write the x up here. I kind of just drag up from where I'm at, like x times what gives me negative 4x. So understand when I do this arrow pointing, I'm referring to this x length as this x length right here. Just like this. This x is also over here. So x times what is negative 3x? That is x minus 3. Okay. So this does factor out to base times height of this entire area of this rectangle is x minus 4 times x minus 3. This is for part A. In part A, this factored to x minus 4 times x minus 3. Okay. Now, two things I'm going to do and talk about here. Number one is that these, let's see, how do I say this? The two numbers that were here, 12 and negative 7, also appeared right here, 12 and negative 7. This is true for any 1x squared problem. So part A, part C, and part D. The last number, the constant term, is going to represent the product value. The middle coefficient right here for the linear term is going to represent the sum. Not for this one right here, unless we have a common factor, which we don't. The second thing I want to mention is, as long as we have a 1x squared here, these two numbers right here also appear to be the numbers inside the factored form right here. This is always true for a 1x squared problem, such as these other ones that we find here. So I don't have to go to this step for 1x squared problems. I will not in the future. I am only doing it for this first problem here. For part C and part D, I will not do these at all. You're going to have to hear my words and follow the process from there for the sake of time and pacing. Okay. Now, I can clear the stuff out here. It's unneeded for my end here. I just need to keep solving for x. Now, they said use the zero. They said factor and use the zero product property. So they're giving us some statements to use. I factored. Zero product property, what's that all about? Well, this is equal to 0, right? This whole thing's equal to 0. So here, factored to this, now it says equals 0. So let's write equals 0. There's this thing called zero product property, which states if you multiply two quantities together, any two values, and the result is 0, what must be true is that one of these absolutely must be 0. Okay? As long, it's impossible for two non-zero numbers to multiply and become 0. The next thing that's true is that as long as one of these is 0, then the result's 0. Both of them don't have to be 0, just one or the other. This is not true for any other number. 0 is very magical and special in that way. So as long as I have a product set equal to 0, notice it's this times this, A times B. If A times B equals 0, either A equals 0, which is x minus 4, or B equals 0, which is x minus 3. So I'm setting up two equations, and now I can solve this quadratic here. What value do I subtract 4 from to get 0? Well, that's 4. What value do I subtract 3 from to get 0? That value is 3. So these are solving for x here. They ask us to find the roots of the following quadratic equation. These are roots. Excuse me. Roots are the values of x when y equals 0 in an equation. And you don't see a y here, but y would have been right here. Substitute 0 for y. So these are the roots. So another way of saying that is if these are the values of x when y equals 0, if I graphed this equation, there would be coordinate points 4, 0 and 3, 0 that I could attend to. If you want to write your answers like this as well, that's fine. These are also called x-intercepts. They're called roots, solutions, x-intercepts. They're also called zeros. There are a lot of different words for them. So knowing this word is kind of nice. That's part A, factoring and splitting this up. All right, part B. I'm going to speed it up a little more now. Part B, I'm going to do the same diamond and rectangle thing for this. Now, first thing I would look for these problems is there a common factor? Meaning, is there a number I can divide out of every single term and there would still be integers left inside? Like, could I divide all these by 6? No. By 3? No. It's recommended that you do for simplicity purposes. I'll tell you why this number gets a little bigger and harder, because we have these bigger numbers to work with. I know that if a quadratic term appears here, then the constant term appears on the other side. 6 times 20 is 120. I'm going to find two numbers that multiply to become 120, right? Whatever these two multiply to, these two. Guess what they add to? The number in the middle, negative 23. So what two numbers multiply to become 120 and add to become negative 23? That's what we're looking for. Let's list factors of 120. 120 times 1. 60 times 2. 40 times 3. 30 times 4. 24 times 5. 20 times 6. 15 times 8. 12 times 10. And that's kind of it. You know, once you do 10 times 12 and 8 times 15, you're going back to this list again. So there are a lot of factors, right? There are a lot you have to test here. Because the product is positive, either both numbers are positive or both numbers are negative. Because the sum is negative, it must be true that both numbers are negative here. Let's try and subtract these and figure out which one gives us negative 23. And you might see the answer already when it comes to this here. Negative 121. Negative 62. By the way, if you did not come up with the number after this, make sure you found all the factors, make sure you calculated correctly and all that. But if you couldn't, that would mean this is unfactorable. That does not mean, and here's the answer by the way, that does not mean that it's unsolvable. That's say for chapter 9, but it does mean that it's unfactorable. So negative 15 minus 8 is negative 23. Boom, chicka boom. So this will be negative 15x and negative 8x right here. Okay? So that's the first set of trial and error you have to do, listing until you find them. Here's the next set. Remember when we list the factors out here, we're trying to come up with two numbers that multiply to 6x squared, and then you got to multiply these ones out as well. So let's see, 6x squared, you could do 6x times 1x, right? And 1x times negative 15 is negative 15x. But 6x times what gives us negative 8x? Well, not an integer. So if that doesn't work, then this isn't the true set. There are other sets we can try. Let's try 6x here and x here. 6x times x is 6x squared. 6x times what is negative 15x in this case? Well, again, issue. There's an issue there. It's not this either. What else multiplies to 6? 3 times 2. 3x and 2x. 3x times, 2x times, this must not be it either. There must be one more here. How about 2x and 3x? 3x times negative 5 is negative 15x. 2x times, 4, negative 4 is negative 8x. So this seems to work here. And by the way, the last check, which I didn't do this last time, negative 5 times negative 4, that's the positive 20. So that seems to work as well. So this all factors down to this right here. So the factored form of part B. Factored form of part B is 3x minus 4, your base, times 2x minus 5, your height. And that is factored form for part B there. This is set equal to 0. Now I have to continue solving using zero product property like I did last time. So I'm going to go ahead and do that right here. Let's keep moving this. Keep moving it, moving it, moving it. Here we go. Part B. If one thing times another equals 0, this times this equals 0, either 3x minus 4 equals 0, or 2x minus 5 equals 0. Now, what values of x do you have to use here? See, these numbers get a little astray. They're a little different. They're not integers. Add 4 to both sides. Divide 3 from both sides. 4/3. That is one of your numbers there. I bet you wouldn't have found that using guess and check, right? You would have tried 1 and 2 and negative 7 and 4/3, man. That's a different number. Add 5. Divide by 2. Boom, there's another answer. Now, I prefer you write them in fraction form here. You know, I don't want you to say it's about 1.3 or 1.3 repeating. No, it's better just leave the fraction in there. Plus, I think you're better at evaluating fractions if we wanted to double check this. Now, 5 over 2 does reduce to 2.5. That's an exact decimal for 5 over 2. I think you're just, once again, you're just better off leaving it as a fraction. Be consistent. Stick it with that. I believe the answer key in the textbook also shows that as well. So I would stick with that as answers there. Now, what this also means, one more time, like I said in part A, is that these are also x-intercepts. This is where your parabola, remember these are quadratics, this is where your parabola is crossing the x-axis at these 2 points here. So again, one thing you want to refrain from doing, you want to refrain from trying guess and check for 2 reasons. Number one, you might not find any answers at all, meaning I don't know what you would have plugged in to try and, what x's you would have tried to find this before you would have given up, right? Because just so you know, it's possible for a parabola to never cross the x-axis. So there might be no answers at all. And you won't know there are no answers if you try a guess and check that way. Number two, you might only find one answer and be done with it. What if you only found this answer? What if you lucked upon finding 4/3? You would have said, okay, here's my answer. There is more than one answer at times with quadratics, right? What if it crosses through 2 places? Then there's more than one answer. There are cases, though, where there is only one answer, and we're going to run into one of them down here in a bit, part C or part D. You'll see which one it is in a moment. But some of them, there's only one answer. Some of them, there are 2. Some of them, there are none. So use factoring. This process, zero product property is huge. The diamond rectangle stuff, there are a lot of different ways you can factor. And I'd love to teach you a lot of them, especially the mental ones. That's going to get you quickly through this, right? How much time have I spent on 2 problems? Two parts of 1 problem out of 10. Probably like 20 minutes, right? You don't want to spend 20 minutes doing your problems as well. So, have yourself another process if you can use it, like this one in C. C has a 1x squared. That's why I checked this thing off right here. That means that I'm going to do this without diamond and rectangle based on the 2 patterns I mentioned before. Now, the only thing that I'm going to do here that's different is this is missing the linear term. Notice how this has a positive 12x, negative 23x, negative 7x. This doesn't have an x term in it. So I'm going to rewrite it with an x term in it. And I'm not just going to make one up. I'm going to use the one that's here. If you don't see it, that means that term is 0x. Right? If you want this thing to go away, you have a 0 multiplied by that thing. So I'm rewriting this with the 0 there so I can maintain that concept, that question we were talking about. What 2 numbers multiply to become this number and add to become this number right here. So if you use the diamond, it would look like this right here, and you'd find out what 2 numbers multiply and add. Now, I can use it. I'm going to not use it, though. I'm just going to list numbers. I'll even do them mentally for you this time. Try this with me mentally. I need 2 numbers that multiply to 9. 9 times 1 multiplies to 9. 3 times 3 also multiplies to 9. No other 2 integers. No other 2 pairs. Which sets add to 0? Well, remember, this 9 is negative. That means one of your numbers is positive, one of your numbers is negative. Like 9 and negative 1, or negative 9 and 1, or 3 and negative 3. Well, 9 minus 1 is 8. Negative 9 plus 1 is negative 8, and 3 minus 3 is 0. Just like negative 3 plus 3 is 0. So it doesn't matter which order you have the 3's, as long as one's positive, one's negative. Those are your 2 numbers that would show up in that diamond there, right here and here, negative 3 and positive 3. Those are the 2 numbers. Now, it's not really a trick, but whenever your 2 numbers add to 0, that means the numbers are exact opposites of each other. They're called additive inverses. So these 2 numbers here, these are the 2 numbers that you would write in the generic rectangle on the top left and bottom right, for example. Now, why am I not going to do it? Because what did I mention? These 2 numbers here are also the 2 numbers that appear in factored form in your answer. We know factored form has a set of parentheses right here. We set it equal to 0. This is a 1x squared, which means that this is x times x something. In fact, I'll double check this problem with you to kind of show you how I know this is the case. Now, there's a minus 3 in one of these and a plus 3 in the other one of these. These 2 numbers end up being the result. Again, only true when you're dealing with a 1x squared. 6x squared, this wasn't true. This wasn't correct. The 2 numbers that multiplied to become 120 were 18 and 5, or negative 18 and negative 5. right? Those weren't the answer. Those weren't the, I can't undo it, but those weren't the factored form values. So they could be, but they're not necessarily. Okay, how do you know if you're right? Well, you could double check this by distribution. I could multiply x by x by 3, negative 3 by x, negative 3 by 3, and combine like terms. X times x is x squared. X times 3 is 3x. Negative 3 times x is negative 3x. Negative 3 times 3 is negative 9. 3x minus 3x is 0, and you're left with this right here. So again, you go back to where you started, and you've said that you have the right factored form. Now, what's the point of factored form? So that we can solve this. Now, I'll let you know, there's another way to solve this problem here immediately from where you're at without factoring. I'll show you it afterward, but it's more of a highlight for the next chapter. And it's not part of our instructions. They asked us to factor here. So x minus 3 equals 0, and there's one more thing that I want to mention about it as well. Or x plus 3 equals 0. If x minus 3 equals 0, x would equal 3. If x plus 3 equals 0, x would equal negative 3. These are two different answers for this set right here. Either x equals 3 or negative 3. And this will go back to my meaning, the thing I want to say here next. How else can I solve this problem, x squared minus 9 equals 0? Well, the difference between this problem and the other three problems, as I said, is it's missing this x term. That means it doesn't, or it's 0x. That means there's no issue in trying to isolate x, combining like terms, or anything else like that. I can isolate x just fine by adding 9 to both sides. I'll get x squared equals 9. X is now by itself. It has a squared with it, but x is now by itself, and I'm just one step away from solving from this thing. It's taking the square root of both sides. Now, the thing is, the square root of 9 is 3, so you try it in your calculator, you'll get this answer. But notice that there's a second answer here, and if you do this, you might not realize there is that second answer. So there's kind of a trick to this. There's more that I could say on it, but for now I'll just say, think about what two sets of numbers you could plug in for x. When you square it, you get 9. 3 squared is 9, but negative 3 squared is also 9. So you might write, in this case, plus or minus. You'll see this in a bit, plus or minus 3. That's another way to solve this one problem here, but it's not the way it was instructed to. We were instructed to factor and use zero product property. So x equals 3 and negative 3. Once again, these are x-intercepts. These are x-intercepts of this parabola. It's crossing through two places. One more problem. This will be the quickest of them all. Ready? X squared plus 12x plus 36 equals 0. Check this out. 1x squared. That means the two numbers that multiply together are 36. When they add, they become positive 12. Products of 36 are 36 and 1. 36 plus 1 is 37. 18 and 2. 18 plus 2 is 20. Nope. 12 and 3. 12 plus 3 is 15. 9 plus 4. 9 times 4 is 36. 9 plus 4 is 13. Nope. 6 times 6 is 36. 6 plus 6 is 12. There it is. It's the two numbers 6 and 6. And they're both positive. Positive product, positive sum. So 6 and 6. If there's 6 and 6, I know this is x plus 6 times x plus 6. Boom. Now, a couple things here. You could use zero product property and say if x plus 6 times x plus 6 equals 0, either x plus 6 equals 0 or x plus 6 equals 0. In which case, either x equals negative 6 or x equals negative 6. Sounds a bit parroting. Sounds a bit like a broken record that I'm saying that twice. X equals negative 6 twice? That's kind of strange. Why am I listing that twice? Why is this happening? Well, it's the same quantity here. You know, another way you could do this, just like I did the last problem, is we could consolidate this. We could write it as x plus 6, quantity squared. That's equal to 0. How do you solve for x here? Just like the last problem. Take the square root of both sides. So x plus 6, the square root of 0, guys, is 0. It's not plus or minus 0, because 0 is either positive or negative. You subtract 6, you get x equals negative 6. So there's another way of solving the problem, but of course they said use zero product property. Now, the other thing I want to state about this was, look, there is only one answer here. So far, all the other ones we did had two answers. What does a graph look like that has only one answer? A quadratic. That is only one x-intercept at negative 6, 0. Well, it looks like this. the vertex is on that point for x. And then it crosses through a certain y-intercept. Apparently it's 36 right here. I'm not going to deal with that. But parabolas can cross one time, two times, or no times at all. And there are different solution sets there. And doing this factoring thing is a nice big first step in doing it, if it's factorable. All of these problems were factorable. Not all problems are factorable, which is just too bad. There are other methods we'll use in the future, not in this chapter here, when it's not factorable and we have to solve. That's A, B, C, and D. Problem 113, the price of milk has been steadily increasing 5% per year. If the cost of a gallon is now $3.89, what will it cost in 10 years? What did it cost 5 years ago? Okay, see, this is not a quadratic problem. This one is, I want to say geometric sequence. This one is an exponential problem. If something increases 5% per year, that means you're multiplying it by what? Multiplying by, well, 105% increase is the same thing as 105% of. What is 5% more than 100? 105. How do you do that? You take 105% of that number by multiplying by 1.05. If y'all remember this here, whole number for the percent is 100 times greater than the decimal multiplicative equivalent right here. So if I want to increase a price of milk by 5% each year, I'm going to take its price, multiply it by this number, and that'll be what the result is. So if the cost of a gallon is now $3.89, okay, what will it cost in 10 years? So right now it costs $3.89. What will it cost in 10 years? Well, let's take a look at this in like a table. If we call this thing year zero, it's at $3.89. After year one, it'll be $3.89 times 1.05, whatever that number is. I'll get the calculator out in a bit. And second year, you take that number, and you multiply it by 1.05 two straight times, like that. And 3, you take 389 and multiply by 1.05 three times. What's another way of writing 1.05 without writing these over and over? Well, this is 1.05 to the first power. This is 1.05 squared. This is 1.05 cubed. If I want to find year 10, you take the year number and you multiply it by 1.05 that many times. So year 10 will be 3.89 times 1.05 to the 10th power. So let me help you out with a couple of these numbers here. Let me start with year 1 here just to give you a value. And by the way, this is money. So I multiply this thing out. I'm getting 4.0845. Well, they don't say, sir, that'll be $4.0845. No, we're going to take this part out or round if we need to. $4.08 after a year. So I'm going to get as close as I can with this answer here. It's going to be approximate. I'll just round up if I have to. I'll do 3.89. I'm going to multiply it by 1.05 to the 10th power. And I get this number here. 6.336400098. This is a unit in dollars. Well, 0.336 right here, this can round up to 6.34. About $6.34. If you did $6.33, I'm completely accepting of that as well. But this is how much milk will cost in 10 years, man. And you know what? These prices might be raising just like that. Now, this thing can be generalized for any year X, right? What if we were doing for year number X, which sounds strange to you? We'd do 3.89, the initial value. We'd multiply it by 1.05 X times, right? 10 was 10, 3 was 3, 2 was 2, 1 was 1. 0 is actually 0, by the way. 1.05 to the 0 power is just 1. So 3.89 times 1 is 3.89. So here's my equation for this thing. Y equals 3.89 times 1.05 to the x power. They don't ask you to find the equation, but this is useful. Where y represents the number of dollars after x years, x represents the number of years since the milk was $3.89. So what did it cost 5 years ago? Well, 5 years ago before year 0, the year before year 0 was year -1. I know that sounds strange, but that's literally what it is. That's what I would plug in for x here. Now, how do you work this here? You would divide by 1.05, right? If you multiply by 1.05 to get 3.89, well, what's 3.89 divided by 1.05? That number is about $3.70. So this is how much it cost a year before it was $3.89. and year 2 before, year 3 before, 4 and 5, what I'm going to do is divide by 1.05 5 times. Now in the equation, it looks like this. To the negative 5th power, I multiply by 1.05 negative 5 times. What? No, remember how negative exponents work. It's the same thing as doing times 1 divided by this number to the positive 5th power. And that means I'm going to multiply by 1.05 in the denominator 5 times, which is the same thing as dividing by 1.05 5 times right here. So I don't have to write all that out. I'm just giving you the understanding here. I think there's something on negative exponents that you're going to have to deal with in review. So I'm going to do 3.89 times 1.05 raised to the negative 5th power, and I get the number 3.047, so about $3.05. $3.05 when rounding. That's how much it cost 5 years ago. Okay, so as you can see, the price in milk does more than doubling over the time, over 15 years of time, from this year to this year way down here. All right. Problem 114, use the graph below, as this is below, to answer the questions below. One of these lines represents Feng and one represents Wei. As you can see them labeled. Write an equation for each girl's line. Now, what are we looking at? Time in hours, distance from school in miles. It looks like as time goes on in hours, as they, I guess they're walking or something. They're doing some, riding bikes, excuse me. They're riding bikes constantly. They're riding bikes for like 8 hours. They're like running away from home. I don't know what they're doing. But as they ride the bike, there's this Y value thing that says how far away they are from their school. Okay. And sorry that I'm explaining it before I do all this other stuff, including the equation. I want the equation to make sense what's happening here. It looks like Feng is this one in what's now blue for me. Here's Feng, and it looks like at time 0, Feng is 0 miles from school. That must mean Feng was at school and is leaving school and is doing it at a certain rate. We'll find out what that rate is in just a moment. Wei, on the other hand, doesn't look like she was at school. She was 12 miles away from school. And that's not to say that she goes to the school. Who knows if they even know each other. I guess they meet. But Wei wasn't at school. It was 12 miles away. 2 hours later, she passes the school site, because remember, this is when Y is 0. And then at some point, they're also going to apparently meet, as they're the same distance away from school. Okay. And probably in the same direction, right? When we're talking about negative distance, I said 12 miles from school, right? Let's say this is north and south. And by the way, this is not east and west. This is time. I'm just saying, let's say these compass directions were north and south. Before, she was 12 miles south of school. She gets to school. She's traveling farther north on some path that apparently Feng is also traveling on. All right, let's come up with equations for these lines first, then we'll answer these questions here. Write an equation for each girl's line. I'm going to do Y equals for both of them. Y equals, Y equals. We'll do it for Wei and for Feng. Now, Wei, right here, remember what I'm doing right here, this is a linear equation. So I'm looking at Y equals mx plus b. I want to find the slope and the y-intercept. Wei's y-intercept is negative 12. B is negative 12. All that means in the context of this problem is that she starts at time 0, she starts 12 miles south, I said south, of school. What's her slope? What's her rate? As time goes on, seemingly every 2 hours, how many miles does she travel? Well, you might count up 1 over 1, up 1 over 1, or even up 4 over 4. Don't make that mistake. Look at the scaling. The scaling's different. Rise, run, how much? Looks like you rise from negative 12 to 0. Looks like that number is a 12. And this is 0 to 2, so that's 2. Looks like her slope is rising 12, running 2. That means every 2 hours she travels 12 miles. So every 1 hour she travels 6 miles. Her slope is 6. 6x. That way, when I multiply 6 by x, it represents how far she has traveled in total, where x represents the number of hours in time. So if it was 10 hours later, she would have traveled 60 miles. And distance from school is y. That's Wei's equation right there. Feng, Leaves school, looks to be traveling a little more slowly, otherwise they never would have met. Looks to be traveling a little more slowly. And what you got to do here really is you got to find points where these things intersect best. For example, I'm not going to choose, like I'll choose 0, 0, that's fine. But I'm not going to choose this point right here and pretend like it's maybe 1.5 or whatever it is. No, I'm going to find something it lands on, even like this one right here. Let's go a little farther out just to be interesting with it. Let's go here, where x apparently is 3. It's between 2 and 4. And y looks like it's 12. Okay, so I'm going to rise from 0 to 12. That number's 12. I'm going to run from 0 to 3. That number's 3. Wei starts at 0. Excuse me, Fang starts at 0 plus 0. And she rises 12 and runs 3. Every 3 hours, she travels 12 miles, that flat rate. So every 1 hour, she travels 4 miles. So her equation is y equals 4 times x plus 0. Better yet, just y equals 4x. 2 girls are riding bikes. How fast does each girl ride? Once again, Wei is traveling 6 miles per hour. Every 1 hour, she travels 6 miles. That's for Wei. For Fang, she travels 4 miles per hour. Every hour, she travels 4 miles. I don't ride bikes, so I don't know if that's fast or slow. When do Wang and Fang meet? Fang and Wei meet. At that point, how far are they from school? So they meet at this intersection point right here. You can either take a look at the graph. It looks like the x value is 6. So they meet 6 hours after they start riding their bikes, I guess. And how far away from school? Looks like they're both 24 miles away from school. Now that's the x, y coordinate pair. There's another way of finding it without the graph. And that is by finding out these x and y values when they're together. I'm going to rewrite these two equations here. Y equals 6x minus 12. And y equals 4x. I got to find out when the two x's and y's are the same. You could make a table. You could also solve by substitution or elimination. If y equals this and y equals that, then 4x can take place of this y, and I can make it say 4x equals 6x minus 12. Then this equals that. Boom, set them equal to each other. This is substitution. Subtract 4x, add 12. Divide by 2, we'll get x equals 6. Notice how we get the same x value as we did right here. Same x answer solving it algebraically. How do we get 24? You plug in 6 for x in either equation. 4 times 6 is 24 for y. 6 times 6 is 36. Minus 12 is 24 for y. You get y equals 24. And that answers your question. Sorry about that bell. And that answers those questions there. So when do they meet? 6 hours from hour 0, from when they start writing. How far are they from school? 24 miles, I guess, north of school, if I answer it that way. There we go. Number 115, graph y equals x squared minus 2x. Identify the y-intercept, x-intercepts, and the vertex. Okay, to start off with, this is indeed a quadratic function, which means the result is going to be a parabola, which is exactly why it has something like a vertex right here. And it says x-intercepts as well because it's possible for a quadratic function to have more than one x-intercept. Whereas a line could only cross through the x-axis as many as one time, a parabola can cross through twice. It could also cross through 0 times, understand that, so we might have that answer, though knowing this graph right now, I know we're going to get 2. But it could also have 1. We could have a graph that goes down, I didn't really draw a good one, that goes down and comes back up, and it just hits the x-intercept at the vertex, which would be quite interesting. But that's not what we have here. There's something kind of interesting about this one, and you might already note it by the fact that it only has 2 terms here. Now, you might be inclined to immediately write this like this here, and by all means, this helps give you information. Y equals x squared minus 2x plus 0. Now, the 0 is the constant term. This is the one that gets unchanged no matter what x becomes. Now, that unchanged number is 0, which is kind of strange. This does actually reveal your y-intercept. The value of y when x is 0 is 0. Take a look at this. What if I substitute 0 for x? What is 0 squared? Well, 0. Minus 2 times 0 is 0. Plus 0. Now, it's a coincidence that this number is already 0 because, look, it could have been 7. right? But the fact is this does not get affected by x. These get wiped out because x is 0. This just happens to be whatever that number is. So there's a point on our graph that is 0, comma, 0 right here. That is your y-intercept, the origin. Now that's an interesting point there because that's also one of your x-intercepts, a point that's crossing through the y-axis at 0 for x is also where it's crossing through the x-axis at 0 for y. One of your x-intercepts, just so you know, is going to be 0, 0. Now, was it luck that we found it? Maybe. We still have to find the other one. I don't think solving this helped us find the other one, but this is a good thing to know going into this problem. This should be one of your solutions. Now, how can we factor this thing right here? Because that's what we're going to do to find the x-intercepts. Well, we could take this as a 1x squared problem and say what two numbers multiply to 0 and add to -2. And you can do the diamond and rectangle, and you'll probably be just fine doing that. I'm going to save you some time. I'm going to ignore this 0 now and just look at x squared minus 2x. Because what's the first thing we should look for all the time? Common factors. Is there a number that can divide from both of these things to affect them? The answer is no. There is no common factor. But, there is no common coefficient. But is there a common variable? This has 2 x's multiplied together. This has 1x. If I factor out an x from both terms, I'll be left with inside x times what gives you x squared? X times x gives you x squared. X times what gives you -2x? -2. This factors into x times x minus 2. Now, this is actually factored form. It might not look like two numbers in this quantity right here, but it doesn't have to be. It just needs to be a quantity. A quantity is just a number that can be measured, even if it's an x. We don't know what it is yet or what it can be, but we're about to solve that right here. So this is one of those factored form things where what are we going to do with this? Set this times this equal to 0. Where's 0 coming from? Well, I turned y into 0. And I wrote the 0 over here instead. It's just a perception thing. I just prefer it to be over there. But what you're looking at now is a zero product property. If one number times another equals 0, either this one is 0, which, by the way, is the answer we have up here, or this one is 0. And what x value would we need for this to be to make this 0? Add 2 to both sides. You'll get 2 for x. So there are two answers there. X equals 0, x equals 2. What are these again? These are your x-intercepts. So let me rewrite them again. Here's 0, 0. Again, it's the value of x when y is 0. 0, 0, and 2, 0. So that's the other point that we didn't have last time. This one here that we did have, it's the same thing, and then this new one right here. Okay, the vertex. The vertex is the point that is either the bottommost point in a parabola or the uppermost point in a parabola. So this parabola might be looking like this right here. In fact, it probably actually does. Or it could go upside down like this. Or it could be very wide like this. As long as it crosses through these 2 points, then any of these parabolas might be. So we got to find that exact bottom point of this vertex. We got to find out where this thing is. So one thing about parabolas that's true is that all parabolas are symmetrical across a vertical line called the line of symmetry. And the line of symmetry is represented kind of imaginarily. Like I could make one right now. And here's how we're going to do it. I'll do it by counting with you guys here. Between 0 and 2 is the number 1. That's halfway between 0 and 2 because it's 1 away from 0 and 1 away from 2. This is the line right here that your vertex is on. This line is called a line of symmetry or an axis of symmetry. Make it a little bit smaller here. Somewhere your vertex is on that line because that's what creates that symmetry, that idea that the left and right are mirror points of one another. Now, how did I find one again? Let me do that one more time for you. Either you can take the average of the two numbers like this, 0 plus 2. That's 1. This is the x value for your vertex. Okay? I don't know what I'm doing right now. I'm just kind of getting that stuff out of the way. That's one way. You could also figure out the distance between 0 and 2. Then divide that by 2 and you get 1. And it's coincidence that this number 1 is here. This number is not the coordinate point, though. This number means how far away you are from here to get to this point, and from here to get to this point. You're 1 away. Either add 1 or subtract 1. Okay. Anyway, so the x value is 1. There's another way we can find it. I'll show you it in a moment. It helps us find y at the same time. So we found the value 1 for x. So it's somewhere on here. What's the value for y? Well, you got to use your equation. Find out what y is when x is 1. Substitute 1 squared minus 2 times 1. That'll be 1 minus 2, which is negative 1. So the x value is 1. The y value is negative 1. Your vertex is at the point 1, negative 1. So it's right here. 1, negative 1. Now, those are only 3 points in this graph. Unfortunately so, that the y-intercept was the same as one of your x-intercepts. So 3 points, it may be enough. Normally, I'd prefer you to find some more, all depending. The thing I just need you to know for sure is this thing will keep going forever. It'll keep increasing more and more. It'll never be vertical. Not very well drawn. And, it kind of takes on this shape. Okay, so those are things you'd have to know. Some things that I'd like you to know as well, though. What if you do get another set of points? So what if you found the one more over here at x equals 3? Okay, now that's not too hard to do. Look, you can do a table, but because it's only one number that we need to find, hopefully you have the courtesy of being able to do some mental math right here. Plug in 3 for x. What do we get for y? 3 squared is 9 minus 2 times 3, so minus 6. 9 minus 6 is 3. So there's a point on your graph that's 3 over 3 up, right there. Now, why is this kind of point important? Because that axis of symmetry thing is so important here. Any value that's the same distance away from the axis of symmetry is the same height. These two x-intercepts are at y equals 0. This point is at y equals 3. Now, where's another point that's on this side over here at the same height? Well, it's going to be the same distance away as this. This is 2 units away from the axis of symmetry. So 2 units away from the axis of symmetry at x equals negative 1 also has the point, the y value of 3. So that's another point you could find. Right? Negative 1 squared minus 2 times negative 1 is not too hard to find 3 either, but that's just another way you could find it. What's another set of points beyond that? When x is 4. 4 squared is 16 minus 8, 2 times 4 is 8. So that's up here, which is 3 away from here. So this point is also 3 away from here. So you're starting to really see that pattern here. And you might be wondering, isn't that just like a table? Well, yeah, it is. I didn't draw out a table. Is one difference. You could draw it out, doesn't matter. But I didn't draw out a table. But the more important thing is I didn't start with the table. And I'm going to talk about that in just a moment as well. First, let me show you the other way to find this vertex right here. Vertex. So I found the vertex here by knowing that the x value is halfway between your x-intercepts. Well, what if you didn't have your x-intercepts yet? Or what if it was hard to find? Or, what if you wanted a different way? There's also this other form that's called vertex form. Vertex form, or graphing form of a quadratic equation, looks like y equals a times x minus h, quantity squared, plus k. A is the same a value in the standard equation. Standard equation looks like this. This a, in our instance, is 1. Okay, notice they don't have a b and c here, though. They have h and k. Why h and k? Specifically, I do not know why they use the letters h and k. But why are they different? Because the numbers represent something different. But the a in one of them represents the a in the other. Now, the h represents the x component of your vertex. The k represents the y component of your vertex. So if we rewrote this equation to be in this form right here, we would be in good shape. So how do we do that? In order to get this thing to be a set of parentheses squared, that means we need to rewrite this thing out as what's called a perfect square trinomial, We've seen this with algebra tiles. Basically, borrowing unit tiles to fill up a square. And whatever we borrow, we return. If I think of this equation back again as y equals x squared minus 2x plus 0, notice how 0 is not the number that helps me make that perfect square. And I'm stating that as if you know what I'm talking about when I'm saying that, because we've done it before. So I'm going to add another number instead right here. This 0 is going to hang outside here like it shouldn't be there. And then a minus whatever I borrow, I'm going to return. So what number am I going to borrow? What I'm going to do is take this number, negative 2. I'm going to divide it by 2, and I'm going to square it. Negative 2 divided by 2 is negative 1. Negative 1 squared is positive 1. I'm going to add this number here, and I'm going to subtract this number here. Whatever I add, I have to subtract for balance. Now, why did I do this? Well, better yet, why don't I just do 1 minus 1 after this? Because I wanted this to be together. I wanted this to be a factorable, what's called a perfect square trinomial. It's 3 terms that make you a perfect square. What's a perfect square? Something that can be factored where the base and the height are the exact same numbers. This is x minus 1 times x minus 1. It's the two numbers that multiply to positive 1 that add to negative 2. X minus 1 times x minus 1 is x minus 1 quantity squared. So this factored to this. Now there's 0 minus 1, which is negative 1. That's still outside here, right there. This is vertex form. This is the equivalent, this is the equivalent of your top equation, your original equation, only it gives you different values. What did I say? The vertex is at h and k. Well, let's take a look at this here. Here's h, here's k, right? This says x minus h. This says x minus 1. H must be 1. The number that I'm subtracting there is 1. This is a plus k. This is a minus 1. So I'm going to be adding negative 1. My k value is negative 1. So your vertex is at the point 1, negative 1. There it is. We found it again. That's another way. Okay, now back to my table talk. I was explaining a little bit that a table might be a bit of an issue to do with parabolas. And although my explanation why won't really work very well for this problem, you have to understand that there are worst case scenarios when it comes to quadratics for tables. Let's think about graphing a line first. Now, you may know how to graph a line really quickly using y equals mx plus b, where you start from the y-intercept, and then you rise and run and plot points, and then you draw your line. I think most of you guys are pretty vested in that kind of idea. Now, if you didn't know how to do that, you could still use a table. You could go to x, y. You could plug in some negative values. You could plug in some positive values, get 0. And then you could also find out what those y values were. Let's say there were 0, 2, 4, 6, 8, 10, 12, etc. And then you plot those points. And what's great about that is that this thing just goes straight. You know it's going to go straight the rest of the way, and there's nothing else to it. Well, a parabola, on the other hand, has features. It goes down, it goes up, it has a vertex, and we got to find those. Now, what if you do that same thing? Only for the parabola, and I'm going to mark it in blue this time, only for the parabola here, you try negative 3 to 3. And then you get points that are like, I don't know, like 47 and like 36 and 29, 24, 21, 20, you know, all these strange numbers here. Maybe 21 back up. Who cares what it is? You get strange numbers like this, okay? Well, your graph from negative 3 to 2 was probably way up here and coming down like that, and you haven't yet found your vertex or anything, right? We don't know where our vertex is yet. They ask us to find it here. Did I see it from this equation? No. If I had this equation, could I see it? Yeah, and I'd have to get to that equation. But from the top, from standard form, I didn't know where the vertex was, right? I could write another quadratic equation right now, like this one. X squared minus 38x minus 360. Okay, now that's not necessarily a fun equation for you to do, excuse me, plus 360. That's not necessarily a fun equation for you to do right now. Okay, I'm not intending you to do it. But how do we find those x-intercepts? Excuse me, the vertex. We have one of two ways, either finding the x-intercepts and then finding the point in between, or putting this in vertex form. And it's not to say that either is extremely difficult, especially without a calculator, but it takes some time. And one thing that doesn't work is you can't just use this table here and plug in these numbers, because what will you get? Numbers that are nowhere close to your vertex, numbers that are nowhere close to the origin. It's just not going to work. So the problem, here's problem number one with the parabola, is you don't know where the vertex is just from your equation. Just so you know, it's at the x value of negative 19. What's the y value? Actually, I think it's still negative 1. I'm not sure. But anyway, the x and y values are not very nice, right? You wouldn't have gone to negative 19 for x to find it. And to find it, you have to go beyond negative 19. You have to go to negative 20 or something. Okay. Here's the second issue, and I'll be sure to undo this and get this graph back. But here's the second issue. Let's say you do your points, you plot your points, and then you end up getting a vertex. Doesn't matter if it's close or far. Let's say it was right here. Okay, so you plot your points, you get your vertex down, here. Okay, then you keep going, blah, 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 blah. Well, and then you draw it, and then they ask you to find the x-intercepts. Look where these x-intercepts are crossing. Right there and right there. It's in between. It's in between two sets of numbers. Now, is it exactly at 1.5? Maybe. I don't think this one is. You'd have to find it, right? So, there are just a lot of different things behind this. What if the vertex is between 2 points? What if it's right there? And then we have other points that are, out here, right? So it's not exactly a pretty way of going about things. So we have much more efficient ways that we can just do mathematically, and then we'll draw it based on the math that we do. And I think that's the best approach we can do. Plus, if you find your vertex, what's that other thing that I said it helps us do? Let's say this is our vertex here, and I know I keep drawing them around the same place. I know these points right here. If this is my vertex, this is my axis of symmetry. What does that mean? 1 over, 2 over, 3 over. I can get those points immediately just by counting, right? So I'd only need one set of points, only one side for it to even matter anyway. Okay, I'm going to draw back this original graph, and I'm going to move on to the next problem. But that covers a lot of different things on this. It covers finding x-intercepts from standard form. It covers when y and x-intercepts are the same. It covers how to get the vertex in 2 different ways. Covered what use a table has for vertexes, for quadratics, and what it doesn't have. Okay. I'm not saying tables are impossible. I really can't draw this part. I'm sorry. Tables aren't impossible to use. If you know where the vertex is, by all means, use a table. Maybe you won't find the x-intercepts you want. Maybe you will. But there are other efficient ways, and especially when you're being asked to label those parts, I would just go for the really the easy route. I would. So there you have it. Number 115. Number 116, find the coordinates of the y-intercept and x-intercepts of this. Show all the work used to find these points. Okay, so we have another one here. It says find the coordinates. It never said graph it. Never said draw a graph. Can you draw a graph? Yeah. Do we have to? No. Last time, how did I find the y-intercept? Well, remember, the y-intercept is the value of y when x equals 0. Substitute 0, substitute 0. We don't substitute anything there. 0 minus 15 is negative 15. The y-intercept is the value of y when x equals 0. That value, the coordinate pair, is 0, comma, negative 15. And guess what? Wouldn't have fit on this graph. It wouldn't have. One thing I do want to mention before I move on here, and you probably see it here as well, the y-intercept doesn't guarantee that your vertex is on the y-axis. So when we found 0, negative 15, if this was the only information I really knew, and negative 15 was way down here, that says nothing about the rest of my graph. Could my graph look like this? I'm sure it could. Is this the way this one looks? I don't think so. It might look like this. It might look like this. Whatever, it might look like this. We still don't know anything. It could look like this. We still don't know anything about this graph yet except the y-axis, and there's no guarantee that that means that's also the vertex. So keep that in mind, please. X-intercepts. Factor. Y equals x squared minus 2x minus 15. Remember, the more I factor with 1x squared, the less I want to do diamond and rectangle. What two numbers multiply to negative 15 and add to negative 2? Here are your factors of 15. The product is negative, which means one of these numbers is negative, one's positive. The sum is negative, which means the larger number is negative. So test both of these, and it looks like it's negative 5 and positive 3. So these numbers, this factors down to x minus 5 times x plus 3. So for x-intercepts, I got to set this product equal to 0. X minus 5 times x plus 3 equals 0. If that's true, then either x minus 5 equals 0, whoops, or x plus 3 equals 0. Once again, only one of these has to be 0. If this is 0, that means x is 5. If this is 0, that means x is negative 3. The x-intercepts themselves are 5, 0, and negative 3, 0. Two of them. And again, x-intercepts are the values of x when y equals 0. That's what I did. I set y equal to 0. And that answered the question, right? Show all the work you used to find these points? All right, I showed it. All of it's there. We're all good. Moving on. Number 117, not much to do with quadratics, although it looks like there's an x squared there. But it has a lot to do with exponents and simplification rules and such. Now, these are old rules from a previous chapter with exponentiation and logarithms. You know, there's one of these that we didn't do very much of, and I'm sure a lot of this is a little old school to you, so let's revert back to some of these here. Let me start with the fraction one, though. This is one you probably haven't seen in a while, or I don't know if ever. I know I've mentioned it. I don't know if I've written it down. Let's say you have a base letter A. Probably should have used B. Let's say I have a base letter A, and we raise it to some fraction exponent, like x divided by y. Without using a calculator, there's a way we can do this as long as we know how to take I'm going to call this the y-th root. Y-th root, you know, like cube root, square root, fourth root, fifth root of a to the x power, or the y-th root of a and all of that to the x power. What that means is I can either take a and raise it to the x power first, and then take the y-th root of that. You're wondering why I'm saying y-th root, what that means. I'll get to that with real numbers. Or I can take the y-th root of a first, and then get a and x, do x second. Does it matter which order? No. You know, just make sure you know what you're doing with it. So let's look at part A right here, part A. I'm going to rewrite this entire thing as far as what I can simplify. 9 to the 1/2 power. Notice how my y is in the denominator in my fraction. That's going to be the number that goes over here. So if the 2 is what's being divided in the fraction, the 2 goes here. And this is 9 to the 1st power right here. A to the x with y. Now when you see square root symbols, you actually don't see this 2 here. It's just implied that it's there. So you can either leave it or erase it, and both of them mean the same thing. Just like 9 to the 1st power is the same thing as 9. So this number right here, 9 to the 1/2, is the same thing as taking the square root of 9. There's an x squared that's being multiplied. There is a y that's being multiplied. Then there's 27 to the 1/3 power. Well, this works the same way as this one did right here. 27 to the 1/3, what I'm going to do is put the little 3 right here. That's called a cube root. And this is of 27 to the 1st power. Now, 27 to the 1st power is the same thing as 27. So I would have to take the cube root of 27. Now, this 3 has to stay here, just like this 2 has to stay here for x, even though a 1 wouldn't have to stay here for y. Square root's implied when it's missing. The cube root, the 3 needs to stay there. This is y to the negative 1st power. Let me write out one of those other properties for you right now. Y to the negative 1st, well, that's not a property. Any base raised to a negative exponent is the same thing as 1 divided by this with the positive exponent. Why does that matter? we need positive exponents in our answer. So y to the negative first power is the same thing as 1 divided by y to the positive first power. Now, does that 1 need to be there? Once again, of course not. But now it's a positive 1, so we're good. Does this look cleaner to you? Maybe not, but we can keep cleaning this thing up right now. Let's go. Square root of 9. What number times itself is 9? Well, that's 3. Cube root of 27. That means there's some number times itself. That's 27. That also happens to be 3. Notice that it's 9 times 3, and 9 is 3 times 3. So this number is also 3. You know what? I'm going to put these right next to each other. Multiplication is commutative, which means I can reorder these numbers. As long as the values stay the same, the result will stay the same. So 3 times 3 is going to go there. Next, I'm going to take my x terms. It looks like there's only one of them, and I'm going to multiply that. And then I'll take my 2 y terms here. Now I have y right here. And right here, I have 1 over y. So y times 1 over y is the same thing as y over y. Y divided by y is 1. So I'm going to cross those out and ignore them the rest of the way. 3 times 3 is 9. My result is 9x squared. That is the final answer to part A. Now, what does this all mean? What this all means, for simplifying, is that if I had values for x and y, like x was 3 and y was 6, and I substituted 3 in for x and 6 in for y in this original expression, and you can try it with a calculator. Be careful with your order of operations here. The number you would get here is the same thing as the number you would get here. Now, there's no y that's dependent here because they canceled out. But you plug in 3. 3 squared is 9. 9 times 9 is 81. So if I plug in 3 and 6 in for x and y right here, I would also get 81. So we wrote a cleaner version of what that was, at least with positive exponents, no less. Okay, that's part A. Part B. Part B also has a fraction exponent. Now, what I'm going to do, though, is, there's a number that's outside here as well. First, I'm going to write you a property. If you have a base raised to an exponent, and that whole set is raised to an exponent as well, that's the same thing as multiplying those two exponents together. I can't get too deep into why, other than exponentiation represents the number of times something's being multiplied. The most I can say right now. So when I have x to the 1/2 power, and all of this is raised to the negative second power, I feel almost compelled to multiply these two. Now, how come? Because of what 1/2 of negative 2 is. I know that 1/2 times negative 2 is negative 1. So this is x to the negative first power, which is awesome. It's not a positive exponent yet, though. We just talked about what it would be. It would be 1 over x to the positive first power, which is 1 over x. And that's what this result is. This is just one way to do the problem. I could have turned this 1/2 into a square root of x. I don't know if I can guarantee that I have taught people enough to know that the square root of something squared is just that thing. But I know that you know how to multiply fractions. So that's my story, and I'm sticking to that one just like that. That's B. C. 1 over 125 to the 2/3 power. Now, I understand this thing says without a calculator, and you know what? Normally, I leave you guys to be pretty calculator dependent. So if you weren't able to do this without a calculator, I understand. I still want you to recognize what it is that's going to happen in this problem. Regardless, I am not going to use a calculator. There are two ways you can go about this thing. The first one involves doing the fraction stuff first, meaning that 3 that's being divided can become cube root of. And you have 1 over 125, and this whole thing is squared. Either this thing is squared or the whole thing here is squared. Now, I can't guarantee that people here would know how to work this stuff out, but one thing that is true is the cube root can go with the 1, and it can go with the 125 separately like this, as long as it's a fraction like this, or even a product like multiplication. This stuff is still squared. Now I can either square it all fully like this. The cube root of 1 says what number times itself is 1. Guess what? That number is 1. What number times itself is 125? Well, they give you clean numbers. This is actually going to be 5 here. Now this whole thing is squared. And if you remember how you work with this here, you can either, I don't want to use the word distribute, but you can take that 2 and square the 1 and then also square the 5. Or it's the same thing as doing 1/5 times 1/5. And you multiply straight across. 1 times 1 is 1. 5 times 5 is 25. Here's one way of approaching this problem. A second way of approaching this problem is doing the 2/3 with both terms immediately. And by that I mean taking 125 to the 2/3 power and doing exactly what I just did right here. Take that 2/3 and bring it to both the 1 and the 125. Okay. Now notice you'll get to the same place that you were at before. This is 1 to the 2/3 power divided by 125 to the 2/3 power. And eventually I take these 3's and I split them up like that. 125 to the 2/3. Let's see here. Oh, see, the squared was right here. I left it on the outside. So right here you can square it, what have you. See, I wouldn't want to square the number 125. To be honest, I don't know what that number is squared. That's why I said you might take the cube root first. But it gets you back to kind of where you need to be there. So a lot of approaches for these problems. I know you feel a little perplexed by them. I understand that. Through a lot of practice comes a lot of good results in the end. So just trying to get familiar with them is really a good hot take. And practicing them over and over is good to stay comfortable with it. If nothing more than for the final. Part D, last one. 8x cubed divided by -2, x to the -2nd power. Okay, this one's going to get a bit messy here. Hopefully not too messy. I have 8 times x cubed divided by -2 times x to the -2nd power. Now I started to separate these a little bit to really show you, especially because we just talked about how we can multiply two fractions. I can split up these two fractions as well. Let's get numbers with numbers. Let's get x's with x's. That sounds good. I can do 8 divided by -2. That's -4. This guy. This guy. You have two options here. And again, I keep saying options. I want you to explore your options. There is another thing that if you divide one exponent by another and they have the same exact base, whether the exponents are different or not, you keep the base and you subtract the exponents. So x to the 3rd divided by x to the -2nd power would be x to the 3 minus -2 power. 3 minus -2 is 3 plus 2. That number is 5. This final answer is 4x to the 5th. One other way of doing this problem is dealing with the negative immediately, just like we normally would. Now I told you that something raised to a negative exponent is 1 divided by that guy with a positive exponent. Well, what if the negative exponent is already in the denominator? Guess what? It's this to the positive exponent. So what's another way I could have rewritten this guy right here? X cubed divided by x to the -2nd power. X to the -2nd power. Well, here, first of all, this is x cubed times 1 over x to the -2nd power. See how I can split this up as well? This can turn into x to the 2nd power. And the only reason I'm showing this one is to exercise the other property that's a lot like this one. What if you multiply two things with the same base? You take the base and you add the exponents. And what is 3 plus 2? Well, that's 5. Once again, if you want to see if you're correct with these answers, use the calculator, not like use it for the problem, but to double check, use the calculator, try a number for x, plug it into this thing, see what you get. Then try it for the last thing here, plug it in, see what you get. Hope for no false positives. That means getting the same answer for both unintentionally. That happens a lot when you plug in numbers like 1, sometimes like 0. Try and avoid those. Try something a little bigger. Two is sometimes fine. Sometimes it's not. But yeah, that's as deep as I'll go with that right there. You got some properties there to work with as well. Quinn. Hey, we have a Quinn. Quinn started off with twice as much candy as Denali, but then he ate 4 pieces. Quinn. When Quinn and Denali put their candy together, they now have a total of 50 pieces. How many pieces of candy did Denali start with? Okay, here's the question. How many pieces of candy did Denali start with? It would be nice to actually just figure out how many pieces of candy either of them started off with, right? We don't know that answer. Something that we don't know is called an unknown. For an unknown, let's go ahead and call those variables like Q and D. Let's not let Q equal Quinn, right? That's not what that means, because what if I get Q equals 5 in the end when it says Q equals Quinn? What could 5 mean? 5 could mean 5 pieces of candy. 5 could mean how old he is. 5 could be how tall he is, 5 feet. 5 could be how much money is in his pocket. Don't just say Q equals Quinn. You're not inheriting any sort of quantity there saying that. Let's define it very specifically. Let Q equal the number of pieces of candy Quinn started out off with. Now that way, if we get Q equals 5, which I don't know I haven't done this before. I don't know the answer. If I get 5, that means 5 pieces of candy. And that's what I'm looking for, defining that variable. And it's very important that you do that for another reason as well. And that we'll jump into that when we make the equations. D will equal number of pieces of candy Denali started off with. Now, in the end, the only answer I need is D. I'm going to use 2 equations with Q and D in them to help me solve for D. I'll talk about processes. I might solve for Q first to even solve for D. But to answer the question, I need to find out how many pieces of candy Denali started with. Okay, we have 2 bits of information here. This thing in purple. Whoa. And then this thing in blue. Okay, I'm actually going to start with the blue one. Probably easier to say. Let's restate this in a little more of a mathematical way. And then let's actually write a math equation based off of it. So this says when Quinn and Denali put their candy together, they now have a total of 50 pieces. Hear me out when I say this and follow my cursor. When I take the number of pieces of candy Quinn started off with and add it with the number of pieces of candy Denali started off with, I will have a total of 50 pieces. What does that sound like? Q plus D equals 50. Tell me anything's wrong there. Take a look at how we define the variables. Take a look at the units here. These are all number of pieces of candy, how many pieces of candy. This looks like this agrees for that blue sentence there. The purple one is a lot harder to come up with. Normally, I ask people to try and use real number examples to make sense of it before they actually just write something. So let's try this. Let's pretend like Quinn had 10 pieces of candy. If Quinn had 10 pieces, how many would Denali have? Quinn started off with twice as much candy as Denali. So Denali would have half as much, or 5. So either you can say you take 10 and you divide it by 2. I'll tell you why you shouldn't do it this way, though. You'll end up with a fraction in your equation. Or you could take the number of pieces of candy Denali had, and you can multiply that number by 2. So in my equation here in purple, what I'm going to do is I'm going to match how many pieces of candy Quinn has with Denali. Q has twice as many pieces of candy as Denali. So you take the number of pieces of candy Quinn has and set that equal to the number of pieces of candy Denali has if you doubled her amount. Q equals 2D. You don't know how many people get this backwards to put 2Q equals D. Okay, but you want to take her number and double it to match his amount. That's what that means there. Now there's something else that they say. Then he ate 4 pieces. Okay. It says then he ate 4 pieces, and it says now when they put their candy together, they now have a total of 50 pieces. Okay. Okay, I messed up a little bit then with what I put up here, because it looks like this Q right here should be not just Q, but after Quinn ate 4 pieces of candy, right? So how do I represent that right here? What I'm going to do is I'm going to take Q, and what if Quinn ate 4 pieces of candy right here? See these 10? What if Quinn ate 4 of them? How many would he have left? I know you know the answer. The question is, how do you get it? You take the number of pieces of candy he started off with, and you subtract 4 from it. Then you're left with 6. Now remember, these aren't the real answers. Or they might be. No, these aren't the real answers. The point is, you can use real numbers to help make sense of what you're doing. So what I'm going to put right here is Q minus 4. Now I'm putting this in parentheses just to indicate this is how much candy Quinn has after he eats 4 pieces of candy. Quinn started off with twice as many pieces of candy as Denali. Then he ate 4 pieces. Now when you take the amount he has left after eating 4 pieces, plus all the candy she has, this seems like Patrick and SpongeBob, right? You know when he eats that candy bar? Not Patrick and SpongeBob. Quinn's number of pieces of candy after he ate 4. Denali's number of pieces of candy, she didn't eat any. Now there's a total of 50. This is your system of equations here. Now we still have to solve for D. Okay. I'm going to just go about it one way here. I'm going to use the substitution method because it's very much set up to do so. This equation has a Q and D in it. If this one didn't exist right here and I asked you to solve for D, it would be impossible to do. It's based on how many Q has. One thing I can do, though, is I can re-express Q in terms of D. What does that mean? It means I can take this letter Q and rewrite it with a D. I couldn't just rewrite it with D. I'd rewrite it with how it's equal to D. How is Q equal to D? Q is literally equal to D. Haha. Q is equal to 2 times D. 2 times D can take place of Q right here. 2 times D is taking place of Q. What am I doing with the rest? I'm going to subtract 4. I'm going to add D. And this equals 50. Okay, now I'm going to solve for D, and that'll answer the question. Now, to restate what this says, if I take Quinn's pieces of candy, which is twice as much as Denali had, and then he eats 4 of them, and then you add how much candy Denali has, you'd have 50 pieces of candy. Whew. There we go. 2D plus D is 3D. Put your glasses on. Add 4. Divide by 3. D equals 18. What is that number? That's how many pieces of candy Denali started off with. So I'm going to write as an answer with units, Denali started off with 18 pieces of candy. And that answers the question that was being asked. How many pieces of candy did Denali start off with? Did it ask how many Quinn started off with? No. Could we find it out? Absolutely. Should we? Probably. It's good to double check your answers. Let's take a look at everything based on that. If Denali started off with 18 pieces of candy, then Quinn is double that amount. That means Quinn started off with 36 pieces of candy. Yes, that means Quinn started off with 36 pieces of candy. So let's see if that lines everything up. Quinn starts off with twice as much candy as Denali. Denali has 18, Quinn has 36, that's twice as much. Check. But then he ate 4 pieces. And I'm assuming they're talking about Quinn. I think Denali's a female. Then Quinn ate 4 pieces of his own candy. He had 36. After he eats 4, how much does he have? 32. Eat 4, 32. When Quinn and Denali put their candy together, they now have a total of 50 pieces. Well, Quinn has 32, Denali has 18. 32 plus 18 is 50. So that lines up as well. I'm confident my answers are correct, as long as this he is Quinn, not Denali. If it's the other way around, of course, I could figure that out with you as well. Right now, I'm going to leave it as that. I believe that's probably what the answer key says. Okay, number 119. Given the 2 points, negative 24,7 and 30,25, what is an equation of the line passing through the points? And is 51,33 also on the line? Explain your reasoning. Like a question, change it to a period. Explain your reasoning. How about an exclamation mark? Explain your reasoning. We sure will. First, we got to do part A. What is an equation of the line passing through the points? Well, a good question also is, what kind of equation do we use for this? This is a line. It's not a quadratic equation. We're back to lines again. This is y equals mx plus b, where m can be your slope and b can be your y-intercept. Now, what I like to do for these problems to start off with really is I like to get a drawing in. I'm sure you probably do too, but I'd have to probably recommend it to some of you guys as you're working on it. Now, why do I recommend a drawing? Number one, to make sure that I'm kind of in the right area for like an answer in the end. Like if negative 24,7, I'm going to call this point A. It's like negative 24 and 7 up. Something like that. Boom, there's A. Awesome. B, 30 over to the right and 25 up. Sure. Let's say it's about right there. Let's say this is B. Because I know like when I get my answer in the end, that's this line. Whoa. That's this line right here in blue. I know what to expect for my answer, like a positive slope and a y-intercept that goes somewhere between the points 7 and 25. Right? So that's, so that's kind of what I'm looking for. That's the first thing. That's one reason why I really like this kind of thing. Second reason is because it actually helps me solve. The graph helps me solve. There are some ways that you can go about lines, to find slope and such and whatever. But if you have a visual of it, it's going to be even better. What am I drawing right now? Well, dotted lines. These dotted lines are representing this kind of right triangle. I called it what we call a slope triangle. A slope triangle determines how much we rise, how much we run, and that division, that fraction, is a slope. Your slope is your rise divided by your run. The larger the number, the steeper the slope. This slope isn't very steep, so the number is probably not going to be very large. It's not even going to be greater than the number 1. Expect a fraction. How weird of a fraction? We'll see. A is at the point negative 24, 7. The y value is 7. B is at the point 30, 25. The y value is 25. I'd like to know how much I'm rising from the point 7 to the point 25. In order to do that, I'm going to have to do 25 minus 7. That number is 18. We have risen 18 units. How much have we run as we've run to the right? We start from negative 24, so it means we got to go 24 over here. Then we go an extra 30. What's 24 plus 30? Or better yet, the actual way of doing this is 30 minus negative 24. Well, that's 30 plus 24, like I said, which is 54. So we run 54 and we rise 18. 18 divided by 54 is not 3, it's 1 over 3. And I'm only stating that because, I don't know, I've seen it happen a lot. What's 2 divided by 4? 2. It happens. This reduces to 1/3. Always try and reduce your fraction. Please don't use a decimal, especially in this case. In fact, most people like fractions for slopes, and then they know how much to rise and run. So your slope's 1/3. It's not a horrific number. It's actually not bad. Now, for our equation right now, we know so far what that y-intercept is. So our equation right now looks like y equals 1/3 x plus b. Now we got to find the b value here, and that's dependent on this slope and some x, y value that we know in our equation. For example, I know that one set of xy values that's on this line is 30, and 25. So if I substituted 35 for x and 25 for y in this equation, I'd have an equation that only has one variable in it, b, and I could solve for it. So I'm going to substitute 30 for x and 25 for y. 25 equals a third of 30 plus b. 1/3 of 30 is the number 10. That's 30 divided by 3. Subtract 10, you will get b equals 15. So the equation, the final equation for y equals mx plus b is y equals 1/3 x plus 15. Not too shabby. That's part A. That answers the question on part A. Y equals 1/3 x plus 15. B is 51, 33, also on the same line. Explain your reasoning. It's possible. It's possible that we could take this graph, go rise 1, run 3, rise 1, run 3, and do it 21 times until we decide whether or not it's an answer to this thing. I think that if you fit this on the drawing the right way, you also might notice that it's not. Here's the thing. This is also an xy value. And like this equation right here, one thing that makes points on the line true is if I plug in an x and y value, it would make the left side equal the right side. For example, look at this point A right here, negative 24 and 7. What if I put 7 in for y, negative 24 in for x, and I just computed this right side. A third of 24 is negative 8, and negative 8 plus 15 is 7. What's true about points on the line is that the left side will equal the right side. So let's try and substitute 51 for x and 33 for y into our equation, and let's see if the left side equals the right side. What was it, 51 and 33? Okay, 33 equals 1/3 of 51 plus 15. 1/3 of 51 is the number 17. Believe it or not, it's actually a clean number. 17 plus 15 is, 32. 33 does not equal 32. No sirree, Bob. No. That is not a point on the line. Is it close? Absolutely. Yeah, it is. But they're asking if it's on the line. If it's 32.99, it's still not on the line. It needs to be 33 on the right, just as it is on the left. Is the point 32? Is the point 51, 32 on the same line? Yes, it is. That's not what they asked us. So explain your reasoning. The math is a clear explanation of it, at least to me. And even showing another set was good as well. Number 120, write the equation of the following two sequences in first term form. We've been using the 0th term. Oh, no, I take that back. These are geometric sequences. Okay. I think we've used a set of both first term and 0th term for that. If you have no idea what this thing's talking about, let me remind you of a couple things. First of all, sequence means a list of numbers. That's what you have here. Here's the first term in the sequence right here. We used t of 1. This is second term in the sequence, t of 2. T of 3 is the third term in the sequence. T of 4 is the fourth term in the sequence. We could describe this is called a geometric sequence. We could describe any geometric sequence with the following formula. To find the value of term number n, I take the first term and I multiply it by some common ratio. I'm going to do this one time less than the term number that it is I'm looking for. For example, if I wanted to find the value of term number 5, I could start with the first term, and I could multiply by a common ratio once, twice, 3 times, 4 times. That would give me term number 5 right here. Term number 5, I multiply by this 4 times, 1 time less than the term number. The term number's 5, I multiply by it 4 times. That's why this is here. This is called first term form. Right here. So how do we use it? How does it work? Well, it's pretty straightforward. We have the list. We even have the first term here. So for A, my first term is 100. Now my second term I get from my first term by multiplying by something. Now I know you might say we're dividing by 10, and you would be correct. We are dividing by 10. But the question is, what is the number we're multiplying by? If 100 times some number r is 10, how can we figure out that number? Well, one way is me telling you that dividing by 10 is the same thing as multiplying by 1/10. That would give you your answer. If you didn't know that, or if it wasn't that easy, let's set this up like an algebraic equation. 100 times some unknown number r equals 10. How do we find r? Well, we divide by 100. Silly. 10 divided by 100 reduces to 1/10. You might put 0.1. That is exact. I'm going to leave it as 1/10 right there. So what's my equation? Well, it's t of n. To find the value of any term number n, I'm going to start with my first term, 100. I'm going to multiply by this common ratio of 1/10. And I'm going to do this exactly one time less than the term number that I'm looking for. That is the answer to A. I could find term number 100 this way as well. It would be an incredibly small number. I'm sure the calculator would probably say 0 because it would give up. But this still qualifies. This still works. It works for the next ones as well. Okay, letter B. Same process. I'll take that back. Not the same process. This is not a geometric sequence. This is an arithmetic sequence. How do I know it's an arithmetic sequence? Well, same way I knew this was geometric. I knew you were multiplying by the same number, but I also knew we weren't adding the same number. What am I adding from 10 to 100? Negative 90. What am I adding from 10 to 1? Negative 9. This one, negative 0.9. The numbers kind of look the same, but they're not. This one, it looks like we're adding the same number over and over. I'm adding negative 50. I'm adding negative 50. And I see that much in a pattern, they have to know that I'm going to assume that the rest is true there. So there's the arithmetic sequence that looks like this here. There are two options. There's only one that we did. This says first term form. I'm actually not going to use that. To find the value of term number n, I start from some before term 0, and I'm going to add a common difference exactly n times. If you want first term form, if you really do, you would start from term number 1, and you would add the common difference one time less than the term number. Both of these give you the exact same answer, especially after you distribute. There are two reasons why I'm doing this. One, I think it's easier. I think finding a term number 0 is a lot easier to find here than it is in geometric sequences, especially if in the geometric sequence the answer is a fraction that didn't exist before. The second reason is it looks a lot like y equals mx plus b form. In fact, it behaves a lot like y equals mx plus b form. So anytime I can, I'd like to think of these things as like a y-intercept and a slope and stuff like that. So let's go ahead and work with that. Now I have to find a term 0. Okay, if I add negative 50 going this way, then I subtract negative 50 going that way. What does that mean? It means I'm adding 50 going this way. This number, term number 0, is 50. That's the term before term 1. This is not an actual number in the list because my list starts when n equals 1 and 2 and 3, etc. My term number 1 is 0. So to find the value of any term number n, I start from term number 0. Sorry, I don't care about this one. I care about this one. Term number 0 is 50. Your common difference is the number I had to come up with. Common difference is negative 50. I'm subtracting 50 each time. So to find the value of term n, I start from term number 0, 50. And I'm going to subtract the number 50 exactly the same number of times as the term number to which I'm referring. For example, to find the value of term number 20, I would take 50. Then I would subtract 50 20 times. I would do 50 minus 50 times 20, which is 50 minus 1,000, which is negative 950. Term number 20 is 950, just by doing that substitution. And that was quick enough and painless enough, and it worked out the way I wanted it to. So this is the answer to B right here. One more problem, or set. Write the first 4 terms of the following sequences. Now, this notation is the exact same thing. A sub n is the exact same thing as T of n. Just like, oh boy, we haven't done recursion yet. You know, I kind of feel bad giving you these problems when I know we haven't really done recursion much. I'll explain what it means, though. Don't worry about that. I'm going to start off with this first problem, though. T of n equals 3 times 5 to the n minus 1 power. Write the first 4 terms of this sequence. First of all, this is first term form. And even if you didn't know that, you can substitute 1 for n to figure out what t of 1 is. Maybe I'll do that the first time to show you that it's 3. T of 1, I know that the first term's 3 based on the equation. But if you don't, let's substitute 1 for n. 1 minus 1 is 0. So this is 5 to the 0 power. Anything to the 0 power is 1, except for 0. 3 times 1 is 3. So your first term is 3. What's the next term after that? Well, it's t of 2. And what I could do is I could substitute 2 into here. But, you know, once you kind of dissect how this equation works, you understand that this is the first term. You understand that this is the common ratio right here. So to find the terms after that, I got to take this number and I'm going to multiply it by 5. Right? So to write this actual list, this actual sequence here, I start with the number 3. That's my first term. My second term is 5 times larger than that. 3 times 5 is 15. I multiplied by 5 once to find the second term. To find the third term, I'm going to multiply by 5 twice from here. Times 5 is 15. Times 5 is 75. And the fourth term? O times 5, I think, is 375. And so on and so forth. It probably keep going. That's part A, first 4 terms. Notice the fourth term, I multiplied by 5 only 3 times. 1 time less than the term number. Okay, part B. This is what's called a recursive equation. A recursive equation. Recursive equation means using, now let's see, how do I say this? Means using your equation to get the next item? I don't really know. You know, there are more complex ways of describing it. Let me kind of just go in terms of our t stuff so you can seem familiar. A sub 1 is the same thing as t of 1, which means value of the first term. Your first term's value is 10. Then they give you this right here. What does this say? Well, a sub n plus 1 is the same thing as t of n plus 1. You probably don't know what that means yet. I'm going to talk to you about that in just a moment. And then it says equals negative 5 times, remember this would be t of n right there. So I have this equation right here, and I have the value of the first term. Here's what this says. T of n says the value of term number n, no matter what n value I choose. For example, I could choose 1 for n. So the value of the first term is 10. So how do I find the value of the 1 plus 1 term? Notice how I plugged in 1 for n. I'm going to take negative 5 and multiply it by t of 1. Well, t of 1 is 10. So I'm going to take negative 5 and multiply it by 10, which is negative 50. What's negative 50? 1 plus 1 is 2. So the value of the second term is negative 50. So what does the recursive equation say? It says take the value. It says to find the value of the next term, the term after the term we're looking at, take the value of that term and multiply it by negative 5. How do you think I'm going to find the value of term 3? I'm going to take term 2, negative 50, and I'm going to multiply it by negative 5. Negative 50 times negative 5 is 250. So as we keep finding those numbers, all I'm doing is multiplying it by negative 5. There's another way of writing it in that first term form. It would look like this. You start with 10. You multiply it by negative 5, boom, to the n minus 1 power. These mean the same thing as long as you know that the first term is 10. These mean the same thing. So let's write out that list. We started off with 10. 10 is the first term in the sequence. What's the next term? Multiply it by negative 5. 50. Negative 50. What's the third term? Multiply that by negative 5. Positive 250. What's the fourth term? Multiply that by negative 5. That's negative 1250. Probably got to use a calculator for that one. Anyway, we won't be dealing too much in recursion, but it doesn't hurt to know that you should be able to decipher what this means if you know what this one means. And if you know how we use n minus 1 up here as well. So sequences, they fly in our faces at times, and they can use different notations. You'll see this time to time as well, but it's comfortable just knowing both of them and being familiar with both. And look, I can transcode them anytime I want to. Bring it from one to the other, or I could do the other way. I personally like this way more, I think, but that doesn't mean this doesn't have its uses as well. Anyway, that's it. Fiend!